Hey team, I'm Maddie. Welcome to ScienceSideUp. And today we're going to measure the speed of light with a ruler. So, why did I bust out my ukulele? Great question. Because we're going to start by talking about basic properties of waves, and I think that sound waves can be easier to understand than electromagnetic waves at first. So we'll actually measure the speed of sound first. Let's get to it. All right, first, a basic equation. Our basic equation for the speed of a wave, no matter what kind of wave it is, right? Sound wave, light wave, waves in the ocean, anything, pressure waves out of earthquakes, they all follow the same equation. The speed of the wave is equal to the wavelength times the frequency. So I wrote this out in words so that we all know what we're talking about. But usually this is going to be written for a sound waves. This will be written like this. So speed, S for speed, L for wavelength, F for frequency, and for light, C, the speed of light, is equal to the Greek letter lambda, which is what we use to represent the wavelength of light, and then nu, which is frequency. Sorry team, I had to put my hair up because down it was rubbing up against the microphone and driving me nuts. So let's talk about stringed instruments, right? One of the great things about a stringed instrument like a ukulele or a guitar or a piano or a violin is that it's really easy to understand what the wavelength is. So we pluck a string. That sounded terrible because I plucked it really hard. We pluck a string, and we can imagine it looking something like this, right? I'm going to draw the string playing. We pluck it, and it looks something like that, and then it's going to vibrate up and down. So maybe it goes like this, and then, right, it vibrates up and down like that. So what that means is that the physical length of the string is half the wavelength. For those of you who remember what a sine wave looks like, right? The full wavelength would be from here to here, from here to here. And so when we pluck a string, we're getting the first half of the wavelength. So all we have to do to figure out the wavelength of my ukulele is measure the string and then double it, and that's the wavelength. So I've got a ukulele, I've got a tape measure, I have a ruler, but it's a little too small. And if we put this up here where the string starts and bring it down here, we get that the length of the string is right about 17 inches. Cool. So the note that I'm playing is a G, and it has a frequency of 392 hertz. So let's call that 400. We're gonna make our lives a little bit easier on the math. All right, so let's write it down. So what I've written on the board is my 17 inches. Oh, we forgot to multiply by 2. I forgot to multiply by 2. So 2 times 17 inches. That'll get us the wrong answer. 2 times 17 inches times 400 hertz. Hertz is the same as 1/seconds. So I just went ahead and did that. And then I'm going to convert this to meters per second, knowing that there's 2.54 centimeters in an inch. Believe it or not, that's just a number I carry around in my head. And then that there's 100 centimeters in a meter. So if we multiply all of this through, I've got a calculator. Gets us 345 meters per second. And if you Google what is the speed of sound in air, you'll get a number that's about 343 meters per second. So we're pretty darn close. And I should mention that the speed of sound through any medium is also a function of temperature. And so that 343, I think, is for room temperature, and it's a little colder out here in my garage. But anyway, we used a few estimates. That was a very rough measurement, right? We rounded on our hertz, and we got the right answer. So that's very cool. So I did that to kind of show you with something very physical how we can measure the speed of a wave. We've measured the speed of sound. Hopefully, I have made you trust in the method that we're going to use. Let's move on to the speed of light. All right, team. If you watched my last video, which involved a ridiculous costume, I recently had some fun at a thrift store, and I found this ancient, ridiculous-looking radio. I have no idea if it works. But let's talk about electronics 101. The reason I needed this ancient radio is because I needed something, it won't even come out, with an antenna. Stand by. All right, we have ourselves a radio. So, if you did not know, the reason radios, especially old school radios, have these like long telescoping antennas is that the radio can pick up signals that have a wavelength approximately the same as the length of its antenna. All right, so we'll bust out our handy dandy tape measure, and we're gonna measure the length of our antenna, right? So this is about 19 inches, let's call it 20 between friends, because 20 is a nice round number. I have no idea if this radio works. We will plug it in and find out. Let's see what happens, team. I got it plugged in. All right, the volume is actually labeled loudness. Well, that's a terrible noise. Nope, that doesn't work. That's a terrible sound. But we can still get the data we need off of this. So we measured the length of our antenna to be about 20 inches. But just like we did with the ukulele, for the wavelength, we're gonna double that because the length of the antenna represents half of a wave. And that's because what happens when a radio wave comes in is it actually physically vibrates the antenna, and that's how the antenna picks up the signal. So it vibrates, actually you can think of it in the same way as the string on the ukulele. So our wavelength is 40 inches, and that's about a meter. And then to get the frequency, we're going to not turn this thing back on ever again, ever, but we can look at it and it'll tell us a range of frequencies. So our frequency range that can be picked up on this radio, or could have been picked up on this radio back when it worked, is gonna range from 550 kilohertz to about 100 megahertz. So we've got our wavelength and our frequency. Now we can go ahead and calculate the speed. We're gonna go ahead and use the 100 megahertz as our frequency. So you should know that 1 megahertz is 10 to the 6th hertz. That's a million hertz. And so you'll see me do that conversion when I write it out on the board right now. So we get a number that's about 10 to the 8th meters per second. And if you guys know, the speed of light in a vacuum is 3 times 10 to the 8th meters per second. That's also a number that I carry around in my head. It's come in useful in many a physics class. There, guys, we did it. We calculated the speed of light, at least something pretty darn close to it, with nothing but a broken radio from a thrift store and my measuring tape. So huzzah, go us. I hope you guys liked that. That was super fun for me. Okay, team, that's all I have for you today. I hope you liked this video. Please like and subscribe. Just click that red button right there, right down below. It really helps me out. I am trying to make it to 1,000 subs this year, and we'll have some, I'm thinking of some fun things for us to do together along the way as we make it to that 1,000 subs. Also, expect really high frequency videos while I am continuously trapped in my house. It entertains me to make them. I hope it entertains you also trapped in your homes as we get through this pandemic together as a community. So stay safe, stay healthy, and I will see you guys next time.